This is Jack Jackson. We're going to talk about isosceles and equilateral triangles today. Remember in our sketch Triangles Ultimate, earlier we looked at isosceles triangles after we looked at the side angle side postulate, and you were able to use the side angle side postulate to prove that if a triangle had a pair of sides congruent, it must have a pair of angles congruent. And if you remember, the way we did that is we basically showed that this triangle was congruent to itself with a reflection by using the side angle side. So this side was congruent to that side, that angle was congruent to itself, and then this side was congruent to that side. So you had side angle side within itself. And so that showed that if it has a pair of congruent sides, it must have a pair of congruent angles. We call these angles down here base angles, the ones that are congruent opposite the congruent sides, and the one that's up here could be at the top, could be turned another direction, it doesn't really matter. But the one that's up here between the two congruent sides is called the apex angle. And of course the corollary from that was the equilateral triangle. If we have two sides congruent, then that makes two angles congruent, but then these third side congruent actually turns out to make all three congruent. Now that we have the angle side angle theorem, we can also prove what's called a corollary. Now just in general, when you have a corollary, if you've got statement P implies statement Q, statement P is true makes statement Q is true, the converse of that is statement Q implies statement P. So if this is our original statement, and this is the converse. So notice in general, usually if a statement is true, that doesn't necessarily make its converse true. For example, if I say, if I win the lottery, I will jump up and down and say, Yahoo! But the converse is, if I jump up and down and say Yahoo, then I'll win the lottery. I wish that was true, but the converse is not true. This original statement probably would be true. But in the case of the isosceles triangle theorem and the equilateral triangle theorem, the converse is true. So part A is the part we already did. Part B is going backwards. So if we're given that there's a pair of congruent angles, can we prove that this triangle must have a pair of congruent sides? And we can. The way you do it is you show that this blue side is congruent to itself, and then this angle A is congruent to angle C, and then the side's congruent to itself, and then angle C is congruent to angle A. So again, this triangle is congruent to itself with a reflection, but it's proved by the angle side angle theorem, and therefore corresponding parts of congruent triangles are congruent, so the two sides are congruent. So IFF is short for if and only if. Okay, in fact, maybe I'll write that down. That means if and only if. So a triangle is isosceles if and only if the angles opposite the congruent sides are congruent. In other words, it has a pair of congruent sides if and only if it has a pair of congruent angles. And of course what that means is for equilateral triangle then, a triangle is equilateral if and only if it's equiangular. And you can see the proof written out there. But basically what it says is if you've got all the sides congruent, you have to have all the angles congruent. But then it also works backwards. The converse is true in this case. If all the angles are congruent, then all the sides are congruent as well. So isosceles triangles and equilateral triangles are interesting objects there. And so it turns out that if you start with a pair of congruent sides, then you get a pair of congruent angles. If you start with a pair of congruent angles, you get a pair of congruent sides. If you start with all the sides congruent, then all the angles are congruent. If you start with all the angles congruent, then all the sides are congruent. And of course, by the way, remember an equilateral triangle then, since it's also equiangular, all the angles must measure pi over 3 radians or 60 degrees.